wafer bonding and packaging of MEMS is a very important topic, because in this particular point there is a lot of difference between the conventional VLSI bonding and packaging and MEMS devices bonding and packaging. In case of VLSI, we have seen that bonding means the silicon chip is bonded with the encapsulation, and after that you go for the wire bonding to different leads. But in case of MEMS, it is not the same as the VLSI chip bonding and packaging. The major difference here is that in case of MEMS, 2 or 3 even multiple layer of wafers has to be bonded together to get the complete structure, and in that case the total thickness of the wafer will be more than 1 millimeter in some cases. In that case, the total height of the device is not very small. And another point, in case of MEMS devices, in many applications you need the outside environment should be reflected into the devices. For example, in case of pressure sensor, the bonding and packaging should be such that the device should be exposed to outside pressure or environment. In case of optical or thermal sensors, the complete device should be exposed to thermal radiation or optical radiation. So, in those cases a special kind of bond and packaging is used in MEMS devices. So, that is one of the point where lot of R&D is going on, and in case of MEMS devices the package are not unique, means a special type of package, normally TO5 or DIP, which is available in case of VLSI, directly may not be used in case of MEMS. So, since the requirements are different, you have to satisfy a lot of special aspects in case of MEMS. So, each device require custom package, and the wafer bonding technology is again very crucial, because in case of harsh environment or lot of mechanical movement or agitation like the acceleration sensor, rotation sensor, if the bonding between the wafers are not rigid, then during the course of operation they may come out and total device may be destroyed. So, because of all these reasons, this particular topic in MEMS, that is bonding and packaging of MEMS, is getting lot of importance, and lot of R&D is going towards these directions. So, now today we will discuss in detail, in depth, the bonding mechanisms which are followed in case of MEMS and what are the different kind of packages used. So, assembly and bonding, that is the basic objective of today's lecture. Actually, since it is a micro machine devices, so there will be some mechanical movement among the different components of the devices. So, those mechanical movements should not be disturbed by the package itself. So, it needs the assembly of the individual components formed using micro machining technique. In this case, the wafer bonding in conjunction with micro machining allows the fabrication of 3D structures that are thicker than a single wafer. Basic 3D structure means here apart from the x and y direction, the thickness direction which we call as a z direction, that is not very small, it is very large, because you are going to bond several layers of wafer. And by bonding multiple wafers, sometimes you can get improved performance and functionality of the devices, and it's obvious that the MEMS wafer bonding is highly critical in some cases. There are various processes normally used to develop the bonding mechanism in MEMS devices, and in case of the MEMS devices, not always you are going to bond silicon to silicon. In many cases we require bonding between silicon to glass, silicon to nitride, nitride to nitride, oxide to oxide, glass to glass. So, various kinds of the levels of wafers are bonded together. So, in this particular area we normally use 3 to 4 kinds of bonding mechanism. First one is bonding of hydrophobic wafers, second is intermediate layer bonding, and those intermediate layer bonding several techniques are there, namely eutectic bonding, polymer layer sometimes used for bonding between the two layers, that is photoresist also used where you do not need very hard bonding, soft bonding you can make use of photoresist. Thermocompression layers, thermocompression means you have to press in presence of certain temperature, high temperature and press, that is thermocompression bonding, and solders. In some cases you can just use some solder materials to bond the wafer with some other say package or housing. Third one is important, fusion bonding, sometimes it is also called as direct bonding, and here the substrates are meeting together, they contact each other, and then you have to go for thermal annealing. That is the major steps in case of fusion bonding or direct bonding. And the last one is anodic bonding, which is very important and highly promising in case of the wafer bonding technology of MEMS, and there you need an electric field as well as temperature. So, that is the anodic bonding. So, all these bonding techniques I will discuss little bit in detail in this lecture. Now, first let me give you some examples of sensors which uses the wafer bonding. Here the picture is basically a pressure sensor from Motorola, is a device which has been available in the market, which is at the present available in the market. So, here the bonding is done with the help of some glass frit. What is the glass frit? Basic glass powders which has got very low melting point. So, what has been done here you can see. So, bottom wafer is the silicon constant wafer and the top is the silicon wafer where you have made the devices. So, here is the etching. So, 25 micron membrane is there. So, basically this wafer is a pressure sensor. So, there is a strain gauge piezoresistive kind of thing. So, here is a resistance value is there, metallization is here. So, now top there is a thermal oxide passivation, and now the whole wafer is bonded with the bottom wafer with the help of the glass frit. So, some glass powders are distributed, and then you put the top wafer and use certain, and you apply certain temperature or anneal it, so that the glass frit will be melted very low temperature, and it will help adhesion of the top silicon wafer and the constant wafer. So, this is one technique which is used in earlier days, that is glass frit silicon to silicon bonding, both the wafers are silicon. Another example I show you, that is a accelerometer sensor from Lucas Nova. Lucas Nova is a company and they are marketing this kind of sensor. Here they use glass to silicon bonding. So, you can see here the bottom piece is glass, and already I discussed the accelerometer design and technology in earlier lectures. So, this small groove is made in the glass, that is for damping and overrange protection, and here this is a probe mass, here is the sensing resistors. So, here you can see they are going to use here basically 3 pieces. One piece is the middle, and in the that is the frame only, bottom is the glass, and the top is again you can see the sensing material, which is a small silicon device where you have seismic resistance is there and the silicon mass is there, and here is the silicon bond line. So, and this particular thing has been used for overrange stop. For example, the silicon mass suddenly goes upward. So, this particular portion will hit here and it will be protected before breaking at this at the flexure point. So, that is overrange stop. So, now in the top one, which is silicon, and bottom and the middle is also silicon, middle means frame is also silicon. That means the top silicon and middle silicon bonding, and another one is a middle silicon and bottom is a glass, silicon glass bonding. So, here you are facing the two bonding, one is silicon, other is the silicon glass, and in this case normally they use fusion bonding. Fusion bonding, its specific features and its mechanism will be discussed in future slides. So, this is one example, and third example I am showing, that is for microfluidic channel. So, here only silicon and glass bonding. So, microfluidic has got tremendous application in case of fluidic sensor as well as in biological sensor. So, flow channels has been created over a small area with some nozzles, that is the microfluidics. So, channel is made in silicon. First you make some groove, and the top is the glass plate where you make some hole. Here is one hole and in the right side there is another hole. So, in one hole is used for input flow, inflow of the liquid, and other is the outflow of the liquid, exit. Okay. So, now and in the bottom is the channel. So, in this way just you etch or delineate the silicon wafer, and then in glass you make some small holes, and now you bond the top glass and bottom silicon together, so that you can have the microfluidic like this, very simple microfluidic structure. Here you need silicon to glass bonding. So, that is why these are few examples of the bondings. Now, I will show you some devices which has been bonded, and smart devices so called, because they are going to use the peripheral circuits also side by side. Now, this is the ADXL 78 and 278, the chip, and that particular chip is very popular, and one of the major application is there, and many places, many lot of applications of this particular chip. And here from analog devices, here you can see the package is not similar to any VLSI chip package, it looks like some custom package, and you can see here the lot of circuits are there at the periphery of the MEMS devices, and this is also another design 278. So, there also these CUM type of accelerometer chips are made at the central region, and peripheral regions, a lot of circuits are there. So, this is a complete device. Another is the multi chip and single chip. There are two kind of approaches in case of the MEMS device bonding. Single chip means there you can have the circuit, and in the central region the MEMS devices all are made in a single monolithic piece, but in other is a multi chip means in the package you have used two small pieces where those are interconnected inside the package, and then you can go for wire bonding. So, that is known as multi chip, or sometimes it is known as MCM or multi chip module, and sensor part and peripheral electronic circuit parts are all assembled inside the package, and they are bonding respective places. So, that total chip will be functional if you just use the external pins. So, these are two the examples of commercial MEMS devices which are bonded and packaged. And now, this picture shows the package evolution in case of MEMS devices, in particular accelerometer devices. So, here you can see the first one is a header kind of package. So, the X in millimeter, Y in millimeter, Z in millimeter, all in millimeter. This is the dimension 10 millimeter by 10 millimeter, and 7 millimeter is a Z direction dimension of this kind of package. Now, after that people are switched over from this header type to Sardip type or Carpac type. So, SARDIP or carpet type of package looks like that, which has been shown in that the multi-chip module package in the earlier diagram also. So, this is the 10 by 10 and thickness has reduced from 7 to 5 millimeter. Then this is known as LCC package. So, this looks like that, because you can, if you go from the header type to the recent ones, you can see gradually that chip size and dimensions are going to reduce day by day. So, this one is LCC package, and after that is a LCC is a 5 by 5 millimeter by 5 millimeter and 2 millimeter thickness. Then QFN package is a 4 millimeter by 4 millimeter 1.45 millimeter thickness, and the last one you can see WSP package, and that package is 2 millimeter by 2 millimeter and the Z direction thickness is close to 1 millimeter. So, that means basic objective is to reduce the size of the chip as well as thickness dimension should be reduced, so that it should be much smaller and smaller, but not at the cost of performance. Performance has to be maintained, and at the same time package size and weight should be reduced. That is the objective of the evolution of newer and newer packages. So, now let us now concentrate on the different class of bondings. So, first one is hydrophobic bonding, hydrophobic wafer bonding. Let me discuss. So, here basically two hydrophobic silicon wafers, if you keep one after other and if you press gently and leave it the wafer for some time, it will be bonded, and that means you are not going to use a special kind of gadgets or machine to have bonding between the two wafers. Just hydrophobic silicon wafers you are taking and putting one after another, but in between a hydrophobic wafer always there will be some native oxides that will be there, very thin layer of oxides will be there, native oxide, and now you just put one after another and little bit pressed and at a particular temperature, that temperature is not very high. So, the wafer will be bonded, but the problem is this kind of bonding is very weak bonding. You cannot have the bonding strength, large bond strength in the hydrophobic bonding. So, that is why this kind of bonding mechanism is not used in many of the MEMS bonding and packaging technology. Now, in case of the hydrophobic wafer bonding, the bonding energy is nearly 26 millijoule per meter square, that is the bonding force or bonding energy. Now, it has been observed that the hydrophobic bonding temperature, if you go on increasing, so bonding strength also increases. So, for example, if you increase the temperature from 400 degrees C to 600 degrees C, that the bonding strength or bonding energy will increase 26 millijoule per meter square to 2.5 joule per meter square if you raise the temperature from 400 to 600 degrees C. So, that is one of the thing, but the problems are manifold, that you cannot raise the temperature as you like, that can create other problems. I will highlight those problems in next slides. Now, the fusion bonding is a direct bonding and it is possible only on certain conditions. What are those conditions? The surface micro roughness or smoothness should be very small in case of fusion bonding. That is the second kind of bonding other than hydrophobic wafer bonding. It is basically extension of hydrophobic with certain precautions and certain modification, that is the fusion bonding. So, here the smoothness or micro roughness of the surface should be less than 10 angstrom RMS value, then the wafer bonding will be very good, and at the same time the radius of curvature of the wafer should be very large. That means the wafer wrap should be less than 5 micrometer. So, these are the two criteria for fusion bonding. The process of wafer fusion bonding is basically mating together of a pair of wafers. Two wafers are in contact, and before contact you have to clean it thoroughly, and you make contact of the two wafers at room temperature, and then the combined pieces are treated at high temperature for annealing. Thermal annealing is followed at a temperature between 700 to 1100 degrees C, and in this case of fusion bonding you can get silicon silicon bonding, silicon oxide bonding, silicon nitride bonding, oxide oxide bonding, and nitride nitride bonding. So, all kinds of bondings are possible in fusion bondings. Now, what are the mechanism of the silicon fusion bonding? The wafers adhere at room temperature via hydrogen bridge bonds of chemi-sorbed wafer water molecules that subsequently react during the annealing process to form SiO-Si bonds. Details the chemistry or structure I will show you in the next slide. Basically, as I told you, this kind of bonding they are initiated with the H2O molecules. So, they basically, this is known as chemisorption. You are not putting H2O molecule, but from the environment there they absorb some of the H2O molecules, and the H2O molecules at the interface, means the wafer to wafer, the interface there they are separated by hydrogen atom, and subsequently react with the silicon, and as a result of which from H2O oxygen is coming out, and that oxygen with silicon they form SiO-Si, this kind of bond which are very rigid in nature. This is the basic mechanism in the fusion bonding. High annealing step is necessary here to increase the strength of the bond. 800 degrees C anneal results in sufficient bond strength for subsequent processes such as grinding, polishing, and etching. Now, in many cases of MEMS devices, you need for polishing the wafers as well as you need grinding of the wafer. That means you are going for some mechanical agitation. Your total structure will face certain mechanical agitation, and because of that you need a very good and strong bonding strength. So, for that you need to treat the complete bonded wafer at a very high temperature, that is known as a high temperature thermal anneal, and it is normally more than 800 degrees C. Now, the mechanism, bonding mechanism is further shown in this diagram, and here you can see there are 2 or 3 kinds of steps of reaction are taking place. One is in the range of 200 to 400 degrees C. Now, when temperature is more than 200 degrees C, here you can see you can show this particular diagram which is shown here is when temperature is greater than 200 degrees C. This is the oxide surface, and here is the silicon, and you see this is the bonding surface. Now, what happened, the silicon, and this is silicon and silicon, here is silicon and here is silicon. Now, the gap between that is 7 angstrom, only very few gap, and that is the native oxide, and that oxide which is there on silicon surface, they absorb the H2O molecule, and after absorption by H2O molecule, the H2O is decomposing the oxygen hydrogen hydrogen bonds. So, at low temperature, when temperature is 200 to 400 degrees C, you can see the bonding surface, it is basically predominantly dominated by hydrogen 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 bond. This particular region you can see it is basically the hydrogen hydrogen bonds. So, now if you increase the temperature to 700 degrees C, then you see it is not hydrogen bond, they are forming OH ions, OH. So, these OH groups are created, and the OH together SiOH, then OHSi, you can see the silicon and OH and another OH and silicon. So, they are forming, and this is silicon OH and OH silicon are bonded together, and there the gap between the silicon here and silicon here is only 3.5 angstrom unit. It is much more closer when T is greater than 700 degrees C. So, when the bonding is between hydrogen and hydrogen, that is not very strong, is relatively weak, but when bonding is OH versus OH in between silicon, two silicon atoms. So, bond strength is much more. Again, if you go on increasing the temperature more than 700 degrees C, the H2O molecule is liberated and it direct bond between SiO units. As a H2 molecule at higher temperature, oxide can flow and provide better contact bonding. At again still higher temperature, the oxide itself can flow between one surface to other surface along with the H2 molecules, which will help much more strong bond between the one surface to other surface. In the left hand side diagram is also shown, you can see here the silicon dioxide, This silicon dioxide is very thin in layer. I told you the separation here is 700 angstrom and here separation is only 3.5 angstrom. So, that means here the SiO2 and SiO2 is the native oxide, that is a few angstrom, 2 or 3 angstrom like that. Now, after bonding you can see the interface is merged, both are becoming silicon dioxide, here silicon in silicon, so single piece you are getting here. So, after bonding, now is a chemical structure is shown here. This particular case the hydrogen and hydrogen domination, and here you can see the in some of our hydrogen and then oxygen. If you go for higher temperature more, then you can see SiO and Si, which is the desired SiO and Si bond. Here is also SiO and Si bond you are getting. So, this is a in this particular case you get this kind of the bonding. Ultimately, we look for the not HH hydrogen bond, not OH bond, but SiO and Si bond, that is much more stronger bond. So, now okay. So, next slide shows the problems of high annealing temperature. Now, in fusion bonding we found that temperature should be greater than 800 degree or 700 degree centigrade, so that the bonding strength is very good. But there we face certain problems. What are the problems? Those are highlighted here. The one problem is doping profile broadening. You know, when the temperature is more than 800 degree C, to say in some cases you go for 1100 degree C. So, doping profile broadens because the dopants which are there in the devices, either P plus region or N plus region. So, they start lateral diffusion, some are out diffusion. So, profile may change, that is not desirable. Second one is the thermal stress. At high temperature, obviously when you go for high temperature, then coming to room temperature, the stress development will be higher because of high temperature, and then coming to low temperature you require a special kind of the thermal cycle of the high temperature to low temperature. So, otherwise lot of stress will be developed. Defect generation, and high temperature there are possibility of generation crystallographic defects. Contamination because at very high temperature the many of the impurities are mobile in nature, and lot of contamination may disturb the or may destroy the quality of the devices. And last 2 points are again very crucial. What are those? It limits the use of compound semiconductor, because you know compound semiconductor basically are combination of different elements, for example gallium arsenide, indium phosphide there, but there at high temperature the composition will not maintain, because in case of gallium and arsenide, gallium and arsenic has got different evaporation point. So, if at high temperature the stoichiometric ratio of those compound semiconductor elements will not maintain, they will change because of different melting point or different evaporation point of different elements in the compound mixture. So, that is one problem. In case of the compound semiconductor materials, you cannot go for bonding which require temperature in the range of more than 700 to 800 degree C. And the last problem is there, that is the metallization, because if you go for bonding after metallization, then you know the in all cases of metals the annealing temperature is nearly 450 degree C, and above that temperature the metal film which is used for contact and interconnects, they become soft, and they degrade the quality. If the metal is which is used for contact and interconnection is soft, then after that if you go on increasing temperature, they will evaporate and they will agglomerate. So, because of that problem, after metallization any of the wafers should not be treated at temperature more than 450 or 500 degrees C. But fusion bonding we saw that is required temperature is nearly more than 800 degrees C. So, in that case you will have lot of problem if you go for wafer bonding by fusion technique after finishing the metallization, then after completion of the metal and interconnect lines. So, those are serious problems. So, people are looking for a low temperature bonding technology which will serve all the purposes, which will not deteriorate the quality of the devices, and deterioration means all these aspects which I just now mentioned. So, a low temperature bonding method is highly required for future MEMS wafer bonding technique, and that technique is the anodic bonding technique. Now, bond quality for different annealing temperature, that means what we require for good quality of bond and what are the requirements which will serve all the purpose. Number one is the temperature should be less than 450 degrees C if post metallization wafers are used for bonding, pretty sure, because you cannot go beyond 450 C. But if some wafer you want to bond where there is no metallization line, no metallization contact interconnection there, then you can go ahead at the fusion bonding technique, which gives you a very large bond strength, and you can go easily for high temperature, higher temperature. For example, in case of say the microfluidic channel, so there you are not going to use any metal lines, you are not going to any diffuse lines. So, no diffusion is there, no metal lines are there, you want to have some physical micro channel and some two holes, one is inlet, another is outlet. So, there the fusion bonding technique is no problem, you can go for that, isn't it. So, depending on the application you can choose certain bonding techniques. So, that means where you require the bonding of the wafers after metallization, then you have to use certain technique which does not require the temperature more than 450 degrees C. Now, temperature less than 800 degrees C for wafer with diffusion dopants, that is P plus H top. Some of the cases you require the P plus H top, you have seen that will give you automatic H top mechanism. So, there the problem is even if you do not use metal line, but if P plus H top is there. So, if you raise the temperature above 700 to 800 degrees Celsius, then there is a out diffusion and the H top layer, the geometry or the dimension will change. So, as a result of which you will not get the area of the H layer same as your design, because P plus area will broaden externally. So, in that case you cannot go the temperature higher than 800 degrees C, even the metal lines are not there. The third one is temperature greater than 1000 degrees C for wafer bonding before processing, you can go for where there is no similar P plus layer or diffuse layer, where there is no metal line, but it results in an almost complete reaction of the interface. A 1000 degrees C anneal for 2 hours gives sufficiently high bond strength and is not possible to separate the two bonded silicon wafers without breaking the silicon. That is one of the unique feature in case of the fusion bonding. If you anneal it 1000 degrees C for 2 hours, 1000 degrees centigrade for 2 hour annealing in fusion bonding, the bonding is so rigid, you cannot separate it out until you break the devices. So, that you can use in a specific application where those limitations are not there, which I mentioned just now. Okay. Now, bond quality of different annealing temperature we are discussing. Here some of the structure, anneal temperature and bond strength are mentioned in this table. You can see here the when you can go for silicon and silicon bonding at 450 degree C, bond strength is 0.5 joule per meter square, and void formation, void means what? Non-bonding. Particular points where there is no bonding, they lives with the void, and voids are not desirable, and if lot of voids are there, bonding will be highly weak, isn't it? So, that means percentage of void should be as minimum as possible. So, silicon 450 degree C bond strength is 0.5 joule per meter square and voids is 0.3, no voids are there in that case. Silicon if you go for 800 degree C, then bond strength increases 0.5 to 0.6 joule per meter square and here voids is 0.3%. Similarly, silicon 1000 degree C, you can see temperature you have increased from 800 to 1000. So, bond strength has increased 0.6 to 2.6 joule per meter square has increased and voids remain same 0.3%. Silicon nitride at 800 degree C, bond strength is 0.9 joule per meter square and void is 0.2%. Silicon nitride 140 nanometer, temperature increased from 800 degree to 1000, but here problem is cleavage formation, which is not desirable thing, and voids is again 0.2 formation, 0.2%. Again silicon nitride 300 nanometer at 1000 degree C, again cleavage formation, and voids are 2.5%, not 25, it will be 2.5% non-bonding. So, now we found that if you go for bonding with the silicon nitride or silicon dioxide, one thing is clear here, the thickness of the oxide and nitride has to be very thin. If its thickness increases, then some other thing happens which is not desirable, and so in case of the bonding of the 2 or 3 pieces which are covered with the passivation layer of the nitride or oxide, those nitride oxide thickness should be as minimum as possible, preferably nearly 1000 nanometer and less, 100 nanometer means 1000 angstrom or less. Okay. So, now the critical issues in wafer bonding, and critical issues are namely voids. You should go for certain technique where the formation of voids are as minimum as possible, and from where the voids are formed, these are formed from organic residues, surface defects, inadequate mating between the 2 layers, and by particles contamination. So, before going for the wafer bonding, the surface has to be highly clean, no particle, no organic residue, surface defects as minimum as possible, and it shall be properly mating. Now, both the surface that are fusion bonded have to be perfectly smooth and clean. Next is required optimized processing such as wafer surface inspection, surface pre-treatment. What is pre-treatment? That is hydrophilization, hydrophilic and hydrophobic. So, we need hydrophobic kind of surface and cleaning, mechanically controlled aligned mating in a particle free environment. These are the some points which you must look into during processing of the fusion bonding technique, fusion bonding technology. Okay. Now, there are other several issues are there. Those are namely yield of void free wafers is reduced by wafer bow or defects caused by stress during thermal treatment. Stress generation between the surface is obvious during the fusion bonding at higher temperature. If you go for bonding at 1000 degree centigrade more, and then if the mechanical properties mean thermal expansion coefficient of the 2 layers, if it is a dissimilar material, silicon or glass or silicon nitride with glass, so then if expansion coefficient does not match properly, then there is a chance of the wafer bowing, and that create the defects and which will ultimately create voids and yield will be low. Next one is a bonding of wafers covered with a thin thermal or nitride results in homogeneous bonded wafer. So, that just I mentioned. So, it has to be very thin layer if you go for oxide and nitride. In case of polysilicon bonding, in some cases we also use polysilicon material as a bonding layer. So, in that case a polishing step is necessary to provide two smooth defect free surface. Bonding mechanism is identical to silicon fusion bonding if you go for polysilicon. The technique is almost same. Now, we are switching over to the anodic bonding technique, which is much more promising in case of the MEMS wafer bonding. So, this particular technique is assisted by an electric field. Till anodic bonding, earlier other bonding techniques we never used any electric field. Now, here you require some electric field. In the bottom you can see a pictorial diagram of the anodic bonding technique. So, here the silicon and glass bonding is shown here. Silicon is used as an anode, you can see in the picture, and glass is used as a cathode. And these wafers are kept on a heater whose temperature is raised within 300 to 400 degrees C and voltage is applied. So, now and that temperature you see here 300 to 400 degrees C, it is not above 700 to 800 degrees C, it is a low temperature. Now, if you apply a voltage, then what happens? Glass contains the sodium ions. The sodium ions in the glass, they are drifted away from the interface. What is the interface? Silicon and glass, and silicon is a positive and glass is negative. So, positive sodium ions in the glass is drifted away from the interface, as a result of which a negative charge will be left at the interface. They leave some negative charges at the interface, and these negative charges in the glass, they induce the opposite charge in silicon, and a result of which they create a certain depletion layer kind of thing, and this layer is extremely thin, and because of that a high field is generated at the interface, and that high field basically prompts the bonding process. So, this is the basic technology in anodic bonding technique. The parameters of the or quality of controlling the anodic bonding techniques are time, temperature and voltage. How much voltage you are going to use, how much time you are allowing for bonding, and how much temperature you are allowing. These are the three parameters which control the bonding mechanism. Now, so basically the term anodic bonding refers to the bonding assisted by an electric field. And what are the advantages? Advantages are manifold. What are those? First is the low temperature process, which everybody wants it. Low temperature process means temperature is nearly 450 degrees C. Second is low residual stress, obvious. If the temperature is low, the stress formation will be less, and so defect generation will be less, no bowing etc. Defect generation less means there will not be voids also. Third one is less stringent requirements on the surface quality of the wafers as compared to fusion bonding. Fusion bonding, we told you that it should be highly smooth and smoothness should be less than 10 angstrom RMS value, but here that much stringent condition is not required because you are applying here high voltage. Because you are applying high voltage, the surface smoothness or cleanness point is not that much stringent like the fusion bonding. This is a well developed technology with a high yield if care is taken to achieve a good cleaning procedure and a dust free environment, but people look for dust free and clean environment there. Now, here a typical anodic bonding techniques process is shown here. For example, here is a silicon chip and a silicon dioxide 300 nanometer thickness here, and this is a Pyrex 7740 2.5 micron thickness Pyrex glass. Top wafer is 800 micron thickness. Now, the surface layer in the bottom wafer silicon blocks 380 micron. There you can see the surface layer such as oxide or nitride or polysilicon or aluminum, whatever it is, this is the surface layer, and the support trim is there. They are going to bond together in using the anodic bonding technique. Now, temperature should be less than 400 degrees C, 4 to 450 degrees C as I mentioned, and electrostatic DC voltage applied is 50 to 200 volt from the top and bottom piece. Now, this is the complete picture. So, the hot plate is the bottom, silicon and glass, and you have one thing you have noted down, you are going to use the point contact electrode which is acting as a cathode, point contact, and there it will help the bonding pressure uniformly around the silicon, because bonding pressure is at the tip and that will generate lot of the pressure wave, and that will proceed towards the silicon, so that the total electrostatic, that field pressure is uniform over the entire wafer. So, silicon wafer is placed on the hot plate, a cathode is connected to the uppermost surface of the glass wafer, typical voltages between 200 to 1000 volt, you have to calibrate the whole system depending on your requirement, how much bond strength you need it, and typical process temperature 180 to 500 degrees C. So, here again some things is elaborated regarding the bonding mechanism. What happens at elevated temperature, the glass becomes a conducting solid electrolyte. So, one point, since you are I told you that sodium ions are separated, migrated towards the positive towards the negative cathode. So, the silicon glass wafer which is used at the top as a cathode must be little bit conducting, otherwise the formation of depletion layer of kind of thing will not be possible. It is to be conducting glass little bit. That is why the Pyrex, that 7750 or that model is used, that number is used for the bonding of silicon MEMS devices. And as the sodium ions migrate towards the negative poles, a space charge, which is a depletion layer we say, is created adjacent to the silicon glass interface. Most of the voltage drop is situated across the space charge region, and a high electric field strength between glass and silicon results, because that region is very small. We know the in case of p-n junction devices also, the field is maximum in the depletion layer region. The wafers are pulled into close contact because of that high field. The elevated temperature finally results in covalent bonds between the surface atoms of the wafers. Surface atoms of the wafers will form a covalent bond. So, anodic bonding is possible under atmospheric condition as well as in vacuum. You do not need always in vacuum, in both environment it is possible. So, what are the requirements in case of the anodic bonding? As I mentioned just now, that glass must be slightly conducting, which you are going to bond, it must be slightly conducting in order to be able to build up a space charge region. Second requirement, temperature must stay well above the softening point. Third is, the metal must not inject charge carriers into the glass. If there is metal or in the surface or in silicon, those metals must not inject any charge carriers into the glass, that is another requirement. So, others are surface roughness of the wafers must be smaller than 1 micron RMS. So, there in case of fusion bonding it was 10 angstrom if you remember RMS, but here roughly 1 micron RMS is also okay. The surface must be clean and dust free. The native oxide layer on the silicon must be thinner than 200 nanometer, means 2000 angstrom. The thermal expansion coefficients of the bonded materials must match in the range of temperatures. So, for that I can show you a plot of the temperature versus thermal expansion coefficient. You can see here up to certain temperature 450 degrees C, silicon and Pyrex, the thermal expansion coefficient is almost similar. Corning glass 7740 wafer, which is most commonly used, little bit conducting, this particular the number of Corning glass, Pyrex Corning glass is used for most of the glass silicon bonding in case of MEMS, because there we find that there is a good matching between the thermal expansion coefficient of the two materials. Bonding process limited to about 450 degrees C, since expansion coefficient deviate significantly after 450 degrees C. You can see here the two curves deviate further if you go on increasing the temperature. So, it can use a sputtered glass on silicon and bond silicon to silicon. So, if you need silicon bonding, it require a glass, because the glass sodium ion should be migrated. So, then what you should do, a thin layer of glass is to be sputtered on the silicon, then you go for silicon to silicon bonding. So, it reduces the thermal stresses and it reduces the required voltages also. Now, what are the important effects in anodic bonding? There a DC voltage is preferable over an AC voltage. The advantage of using a point cathode, just I mentioned few minutes back, you require a point cathode. Why? Because in that case electrostatic pressure develops due to the finite conductivity of the glass starting below the cathode tip, and it radially propagates along the wafer. That is the beauty of the point contact cathode. So, anodic bonding is now a well developed technology. This process has a high yield if care is taken to achieve good cleaning procedures and dust free environment, and if polished wafers are used. Now, there are other bonding techniques which I mentioned, intermediate layer bonding. These are very weak, but in some cases that serves many purposes, and we may not go for very good quality the anodic bonding or fusion bonding techniques. They are low temperature bonding basically. Eutectic gold thin layers, eutectic bonding means eutectic epoxy paint, you use it and then you press it, and maybe 100 to 150 degrees C you can heat it and you will get bonding, but that is not very rigid bonding. Solders also used, polymers may be used for bonding, very soft bonding, low melting temperature glass which is glass flits, one example I showed you using the glass flits. Thermocompression bonding, sometimes people use it. Boron oxide as intermediate layer, since it flows at 400 degrees C. Some people are using boron oxide because at 400 degrees C boron oxide soft and it flows, and then it helps bonding the two wafers. Negative photoresist polymers are also used. Sodium silicate is another material which is used for bonding. Now, if you go for characterization bonding, the main failure mechanism is the formation of voids in the bonding. So, that you have to get rid of the voids. Voids are viewed by IR, ultrasound or X-ray topography. You can see to picture, in the left side picture there is no void, and right side picture there are some void, and it appear regions of different contrast. You can see contrast, you can see, so that means here some voids are there. So, with this just we will stop today, and I gave you a small overview of the bonding technique mechanism and which is good, what are the various aspects, and low temperature bonding, high temperature bonding may be chosen for different requirement of the MEMS devices and packaging. So, let me stop here today. Thank you very much. Today's topic of discussion is interface electronics for MEMS. In last few lectures we have discussed on MEMS devices, particularly micromachine microsensors, and one of the basic job of micromechanical system is that it is a combination of sensors, actuators and signal conditioning circuits. So, if we do not think of the signal conditioning and signal processing circuits, then the system is, or micromechanical system configuration is not complete. So, we have to see what are the various aspects of the output signals coming from the transducers, and how do we proceed with those signals before processing, and after processing how those signals are fed to actuators for further functionalization or for further action. Thus, the interface electronics is an important aspect of any of the microsystem, and at the moment lot of work is going on this important topic which is interface electronics. Now, the signal which is received at the output of the microsensors are of particular characteristics. Because of the different nature of the signal obtained at the output of the microsensors, its signal conditioning circuits and will be different. And in most of the cases the signal processing part we prefer to have digital component, digital signal, and we are inclined or we love to process the signal using microprocessor or microcontroller or in a computer. So, there you know the only signal which is digital that can be processed, but sensors signals are not digital in nature. So, that is the reason we have to go for some conversion also. After getting the signal from the output of the microsensor, it has the condition, and then you have to change the analog to digital before further processing with the help of either microcontroller or microprocessor, and the output are taken, and then they will control the actuators and other things. So far as offset is concerned, but temperature compensation is not that much perfect. So, this bridge which we used for our circuit provide differential low frequency less than 100 hertz, low amplitude less than 20 millivolt signal which is to be amplified, and in that case this amplification has been done up to 6.5 volt in chopper stabilized amplifier with R1 R2 or 1 kilo ohm and R3 or R4 with 500 kilo ohm, and the TC 7652 configuration provides a stable output up to 200 hertz. So, this is basically some small example which I are doing here, but that is not the final. You have to design separate blocks using your required chopper stabilization techniques, amplifiers and all other things if you want to have monolithic interface electronic chip for any kind of sensors. So, there is work going on nowadays for universal interface electronics. So, the interface electronic chip can be connected to any kind of sensor, either it is a piezoresistive or piezocapacitive or maybe other kind of sensor, and it gives an advantage that the interface circuit, if it is a universally acceptable circuit, so that means you can reduce the cost point of view drastically if you assemble some microsystem using lot of sensors. So, just I tried in this lecture to give you a small background of the requirement of the interface electronic circuit and some of the solutions what we can adopt for reducing the three things. One is the noise, another is the offset, and another is the reduction of the variation due to secondary parameters. So, these are the three things we have discussed today. So, let me stop here. Thank you very much.